In section 5 of chapter 7, we're going to be taking a new, different approach to radicals. We're going to be doing radicals in exponent notation. It is a different way of visualizing radicals, but we're still doing the same thing we've been doing all chapter. First, I want to start off with a problem that you've all done before, a problem that shouldn't be too much of a stretch. If I have x cubed equals 8, what I'm hoping a lot of you would say is, oh, if I want to solve for x, we would simply cube root both sides. The reason we cube root both sides is because a cube root and a cube, that is to say a third power, undo one another. They eliminate each other. And you would get x equals the cube root of 8 is 2. Yay, we are done. Here's my issue with that. Thus far, your logic as to why cube roots and cubes eliminate each other are largely based in understanding how they operate and less so on an algebraic standpoint. We don't necessarily see why they undo each other. We just comprehend that cubing and cube rooting are opposite operations, therefore they should undo each other. Today, I'm going to show you why this occurs. So I'm going to say, why do square roots and squares eliminate? Why do cube roots and cubes eliminate? Why do fourth roots and fourths eliminate? Why do nth roots and n powers eliminate? Here is why. Radicals are exponents. They're powers. We just typically don't write them in their exponent form. A square root, which as a reminder, is a second root. We just typically don't write the 2. That is the same thing as a 1/2 power. The reason squaring and square rooting undo each other is because if you have a power brought to a power, what we do is we take those two values and we multiply them together. And 2 times 1/2 is 1, and anything to the first power is just itself. The reason why a radical and its power equivalent undo one another is because one is the whole number and the other one is the reciprocal of that value. So a third root, that's just a 1/3 power. So that's just x to the 3 times 1/3 power, which is just x to the first power, which is just x. Number 3, if it's a fourth root is a 1/4 power. That's just x to the 4 times 1/4. That is just equal to x to the first power, which is just x. This works for all types of radicals and their corresponding powers. So if you have an nth root, that is a 1/n power. And if you ever interact with its reciprocal, the n power, those would just turn into a 1. So this is algebraically why radicals and exponents counteract each other. This is an algebraic understanding as opposed to the conceptual understanding many of you had previously. This is really critical because it's going to allow us to start utilizing radicals in a more algebraic framework, which is going to open up more avenues for us going forward. In the problems presented to you in this lesson, there are largely 2 things I'm going to want you to do. First, I want you to be able to convert from either form. That should be something that you are comfortable with. So for problem number 1, I have the third root of 9x. That is the same thing if you convert it to exponent form as 9x to the 1/3 power. That's the same thing. Number 2, I have the sixth root of the quantity x plus 1 quantity. That is the same thing as the quantity x plus 1 quantity to the 1/6 power. Number 3, I have the square root of 8x. That is the same thing as 8x as a quantity brought to the 1/2 power. Number 4 is actually a 2-step process. You could do it 1 step, but I want to show both steps. That's the same thing as that 7x minus 1 to the 2nd power, all to the 1/11 power. But since I have a power to a power, I could take that 2, the exponent of 2 and the exponent of 1/11 and multiply them together to write this as simply as 7x minus 1 to the 2/11 power. Just like how I just got done going from radical form to exponent form, it is equally important you know how to do the reverse of that, going from exponent form to radical form, because there are some hitches that a lot of you tend to make mistakes on that I want to draw attention to right now. Problem number 5. I have the quantity of 5x quantity to the 1/3 power. That 1/3 power applies to both the 5 and the x. That's what the parentheses are for. Therefore, it would be the 3rd root of 5x. This is something most of you do not struggle with. But in the next problem, a lot of you will skip past and make this common error. I have negative 2x to the 1/4 power. Here's what the answer is not. This is what I see most commonly. This is the wrong answer. The reason that's the wrong answer is because the 1/4 power is only attached to the x. It is not attached to the negative 2. Therefore, the correct way of writing this is negative 2 times the 4th root of x. That negative 2 has no exponent. You do not do anything with it. Problem number 7 is another mistake I see. This is the wrong way to write this one. This is also wrong. The reason that is wrong is the 6/5 power only applies to the x. It does not apply to the negative, because negative x is the same thing as negative 1 times x. If I want to apply the power to the negative with the x, I should have put the negative in parentheses with the x. Therefore, the correct answer is negative 5th root of x to the 6th power. That negative hangs outside. And then lastly, I wanted to throw in a really complicated looking one. Here's my recommendation on how to simplify those. Work from the center out. So I have an x squared plus 1. I'm going to take that and get the 3rd root of it. Then I'm going to take that and multiply it by negative 5. Then I'm going to take all of that and bring it to the 4/7 power, which is the same thing as bringing all that to the 4th power and then 7th rooting it. And then lastly, I'm going to add 1. I like putting little ends to my radicals to let me know when it stops. And then I'm going to bring it to the 9/2 power. So I take that entire thing, bring it to the 9th power, and then I square root it. And this would be my solution. Extra complicated, extra extravagant, but I really need to make sure that you know when and where radicals and fractional exponents apply and when and where they don't, because these are really, really easy to misread. They are really, really easy to miswrite. The last thing I want to go over is something that we've done previously. Problem number 1, if I have the 3rd root of x to the 8th power, all of you should know how to simplify that by now without fractional exponents. You should know at this junction, oh, if I want to simplify that, all I got to do is divide the 8 by 3. And that'll tell you how many x's get pulled out. The 8 divided by 3 is 2, so 2 of the x's get pulled out. But when you divide 8 by 3, you would get 2 with a remainder of 2, so 2 of the x's would remain underneath. And that would be your answer. And that is 100% correct. That is an understanding of how to simplify a radical in radical notation. But there is a little gap in that. The gap is, you know to divide the exponent by the index, and the value that you get goes out, and the value that remains stays underneath. The problem with that is, it's just a thing that works because it works. It's something I told you or your previous math teachers have told you, but you may not have ever seen, why does that work? Why do we do division? Why am I taking that 8th power and dividing it by 3 to begin with? The reasoning behind that working comes from fractional exponents. The reason that works is because if you kept this in fractional exponent form, this would turn into x to the 8 divided by 3 form. And x to the 8 divided by 3 form is the same thing as x to the 6/3 times x to the 2 over 3. And x to the 6 over 3 is just x squared times x to the 2 over 3. And that is the same thing as this. I'm not saying you need to learn how to simplify using fractional exponents, although you really should. I want you to understand the connection. The whole reason as to why you could simplify this using this technique, it stems from fractional exponents. Fractions are division. The reason we divide the 8 by the 3 is because that's what happens when you're doing this as a fractional exponent. You're taking the 8 and dividing it by 3. So problem number 2. When we're multiplying two radicals together, we've gone over this in the past. When and where to multiply radicals together. I said in the past, you can only multiply square roots by other square roots. But that's, again, something I just said. I never explained why. Why can't you multiply square roots and cube roots together? Spoiler alert, you can. We just don't have the tools to do it. We will in the next lesson. But why is it we can only combine square roots to each other by multiplying? Because if you write this as an exponent to the 1/2 power, and then I have that 10a to the 4th, b, c to the 3rd to the 1/2 power, the reason we can multiply square roots to each other but not other types of roots, at least for right now at this moment, is because that's a factoring problem. They're both brought to the 1/2 power. Therefore, I could rewrite this as it's all to the 1/2 power. But I can only do that if they're both brought to the same power. That's why you can only combine square roots and square roots, because you need the powers to be the same. But now that the powers are the same, I can combine like terms. 5 times 10, that's 50. A to the 3rd times a to the 4th, that's a to the 7th. B times b, that's b squared. C to the 6th times c to the 3rd, that's c to the 9th. That's still all being brought to the 1/2. I can then distribute that 1/2 all the way through if I wanted. But before I do that, I'm going to split it up a little bit. 50 is just 25 times 2. A to the 7th is just a to the 6th times a. B squared, I'm going to leave the same. C to the 9th is just c to the 8th times c to the 1st power. And the reason I split it like that is because when I distribute the 1/2, I'll get 25 to the 1/2 power times 2 to the 1/2 power times a to the 6 over 2 power times a to the 1/2 times b to the 2 over 2 times c to the 8 over 2 times c to the 1/2. And each one of these things, in large part, can be reduced. 25 to the 1/2 power, that's the square root of 25. That's just 5. Times 2 to the 1/2. Times a to the 3rd. Times a to the 1/2. Times b times c to the 4th times c to the 1/2. And all I'm going to do in this next step is group all the things that have 1/2 powers together. So the 1/2 powers are the 2, the a, and the c. The 2, the a, and the c. And everything else I'm going to write on the outside. 5, a to the 3rd, b, c to the 4th. And now this is just what would happen if I left it in radical form. It would be 5a cubed b c to the 4th times the square root of 2ac. Again, I'm not expecting you to do this mathematics, but this whole process on how you've been simplifying radicals, what I need you to understand is it stemmed from this. You've just been doing this in the background. This is where all these processes and rules and shortcuts that you've come up with, they all came from this. So if you ever ask yourself, hey, can I do this with radicals? What you really should be asking is, does it follow the rules of powers with fractions? If it does, then your rule works. If it doesn't, your rule will not work.